So let me start. Welcome to the scheduling seminar. Today we will have a talk by Carlo Mannino. Carlo is now located at the Department of Applied Mathematics at SINTEF Digital in Oslo. And he is also with University of Oslo. By the name, we feel that he's Italian, right? So he worked a long time as professor of operations research at the University of Roma La Sapienza. And in recent years, he has been increasingly interested in optimization of telecommunications and transport. And for that, he has got several awards by Euro and some Informed Slavery Section Challenge and so on. So he contributed to development of optimization algorithms for automatic dispatching systems currently in operation in several lines in Europe and in the United States. So I think it will be probably one of the most practical talks we had up to now. So Carlo, the floor is yours, and we are very impatient what you will say to us.
Thank you very much for the nice introduction and also for inviting me to all this talk. So it will be a practical, so I will describe some applications, but at the very end, because before the application, there is a theory which is necessary if you want to solve complicated applications. So this is basically also the message of my talk, which is about train scaling, by the way, models, decomposition methods, and practice. So this is in this picture, you see the control center for trains running in Greater Oslo region, which comprises the large station, central station of Oslo, and 10 lines incident to Oslo. And as you can see from the number of people involved, you can understand that the task of scheduled trains and rescheduled trains in real time is not an easy task. In fact, dispatchers must make a lot of decisions all the time about, for example, how to sequence trains in stations, to which platforms they should go, to some extent, even when they should enter and exit the stations and so forth. In particular, when some delays occur, then the task becomes even more complicated, and the dispatchers have to take all these decisions in real time in order to trying to deviate as less as possible from the wanted timetable. Just to give an idea of how complex are these decisions, so you can look at this picture where you see basically a single track line. Still now, most railways are single track, at least the largest say, size of networks. And this means that the track must be used in both directions, and of course there can be only one train at a time on the track, and then the trains must meet in special points called sidings or in stations. And for example, in the figure you see that there are the light blue trains running up and the gray trains running down, and they can only meet in these special points. So as soon as there is a delay, then typically they cannot meet anymore in the points which were established by the timetable. And so the dispatchers must find a new meet point. And for example, if a train, let's say a first train must meet the second train somewhere and wait for it, and then there was a third train maybe waiting for the first train somewhere else, then this delays can propagate along the entire network. And this is actually what happens. As you can see also in this picture, here you have the schematic representation of the central station of Oslo, and here also dispatchers have a lot to do, because they need to basically let trains enter the station, decide which platform they will go, and then also decide basically the entire route through the station. And in many situations, they need to sequence trains in order to avoid conflict between trains. So dispatchers must actually solve a complicated problem, and this problem is an optimization problem, since they want to minimize the delay, the overall delay, or some measure of the delay of the trains with respect to the given official timetable. And then, if you want to let's say automatize this process, then you need to solve an optimization problem, and actually a complicated optimization problem, and as we would see next. So the train scheduling problem actually appears, if you want, in two basic versions. The first is the one I already mentioned. So this is the operational version, the real-time version, which is called train rescheduling or dispatching, which is the one I've been mostly involved. But also, of course, when in train rescheduling, you need to follow or to let's say minimize the deviation from the timetable. But the creation of this timetable itself is a train scheduling problem, very similar to the first one, even though it's played at a different time level, so it's more tactical and strategical. So in any case, the train scheduling problem is a job so scheduling problem, and very similar problems also pop up in different applications in transport, but not only in transport. Just to give an idea about which kind of transport are also, let's say, have the same kind of problems. You have, for example, air traffic control, ship traffic control. Here next should be an example of airplanes running in an airdrome, and again you have the same problems as trains in a station. You need to sequence trains, you need to sequence airplanes on the taxiways or on the runway and decide how to solve conflicts. And also other examples are robots moving in warehouses and so forth. So now I can start to delve into the modeling and the methods that we are using to solve these problems. And I will present several results coming from different sources, and all the references are given at the end of the presentation. So in order to describe the movements of the trains, you need first to discretize the network. And this is done by simply subdividing tracks into elementary tracks called blocks or block sections. And each block can accommodate at most one train at a time. So a train runs through a sequence of blocks. This sequence is called route. And with every train and every block of its route, we associate a variable called schedule variable or time variable, which simply tells the time when the train enters the block. And now, if you consider two successive blocks on the route, then the time when the train enters the next block in its route is at least the time when the train enters the previous block in its route, plus the running time through the block. And this is expressed by time presence constraints of the form, of the classical form TV minus du greater than or equal to LUV, where LUV is the running time. It's blocked. Yes. Okay. So why? So we can associate a graph with every train movement. This graph is called route graph. In particular, we have a node for each event entering a block section, and then we have edges representing the time presence constraints we have seen earlier. So, for example, at some point, the train I will enter the block section D, and then you have that the train. So that there is an edge between from node D to node G to represent the fact that the train will go from D to G, and the time, the running time through D is LDG. So each edge here represents actually a time present to the train. So this is an example of a route of a train through Oslo S. I guess we will use it again later on. In addition to the nodes that we also add another artificial node called origin to represent the start of the planning horizon. And in fact, every time will be basically referred to the time TO, which is the time associated with node O. So, for example, if the train should, for example, start or should arrive in D not before, let's say, 30 minutes from now, then this is represented by a time presence constraint of the form TD minus TO greater than or equal to 30, which in turn is represented on the graph as usual with a directed edge from O to D, and the length of the edge is 30. Similarly, if for example, the train pops up on track A precisely 10 minutes after the start of the running of the planning horizon, then we have an equality constraint, TA minus TO equal 10, which in turn is equivalent to two inequalities, which are represented on the graph by two anti-parallel edges, one from O to A of length 10, and the other one from A to O of length minus 10. So these three edges I just represented here are quite important. They're called timetable or timetable constraints edges because they are mostly referred to timetables and to arrival and departure times of the trains from stations or any other point. So finally, we have the conflicts. So trains compete for the same blocks as we've seen. For example, here in this figure, train A and train J, at some point they will both want to access the track D. So either I goes through D before J arrives into enters D, or vice versa. So in the first case, we must have that train I will enter the next block in its route, G, before J enters block D. And this is expressed by a time presence constraint of this form. Similar, if J wins the conflict, then it will enter the next block on its route, block C, before train I enters block D. And this is again expressed as a simple time presence constraint. So any feasible schedule will satisfy one of these two presence constraints. And this is why the two constraints together are called a disjunctive constraint. And they are typically represented in this form here now. Again, disjunctive constraints can be represented on a graph. The graph is basically made up of the components that we have already seen in the previous slide. So we have a path representing the route of the first train, a path representing the route of the second train, the origin of the planning horizon O, and now a disjunctive constraint it's basically the disjunction of two time presence constraints. So for each time presence constraint, we have an edge, the dashed edge here, to represent the same term. And the pair of these edges is called a disjunctive arc. It was called, not by me, but by Ballas. So, solving a conflict between two trains amounts basically to decide which of the two terms in a disjunction will be satisfied by the final schedule, which means that the disjunction will collapse in some sense to a standard time presence constraint, which in turn is basically represented on a graph by an edge, one of the two edges in the disjunction. So solving a conflict means at the end of the day, deciding which one of the two edges in a disjunction in a disjunctive arc must be picked up. So now, just to state the train scheduling problem in a little bit more formal way. So we are given a network, we are given a set of trains and a wanted timetable, and we want to find the schedule which satisfies all fixed and disjunctive presence constraints and minimize some function f. We are not considering for the moment the routing problem, but we will discuss it a little bit later. We will see it doesn't change very much the model. So just a few comments on the objective function. This is typically non-decreasing with time, since it penalizes delays. And the two most common forms are the one you see in this figure. In particular, on the left, you have that the cost increases. So the marginal cost increases with time, and in the right figure, instead, you have a step function, which basically counts the number of trains which are delayed over a certain threshold. So, for example, in this case, 3 minutes. Every train which is delayed more than 3 minutes count for 1, This is, for example, the one used by the Norwegian operator. So now just to recap, the train scheduling problem can be formulated as a disjunctive program, where you want to find a schedule which will minimize a certain cost function f, and satisfies a certain number of fixed precedence constraints, and a given number of disjunctive precedence constraints. It is well known that train scheduling problem is a job scheduling problem with blocking and no weight constraints. So everything I'm going to say from now on, and even before now, actually applies to any kind of job scheduling problem. Any instance of the train scheduling problem can be represented by a disjunctive graph of this type, where you basically have the nodes V are associated with the events. Then you have a set E of directed edges which are fixed, and then you have a set D of disjunctive arcs. And each disjunctive arc is made of by a pair of so-called conflict edges, the edges which are dashed here in the figure. So each conflict edge corresponds to a specific term in a specific disjunction. Solving the disjunctive problem amounts to deciding for each disjunction which term in the disjunction will be satisfied in the end, and equivalently, this is correspond to picking exactly one conflict edge for each disjunctive arc in the disjunctive graph. So the set of conflict edges which are picked up at the end is called a selection, or a complete selection, because we are considering all disjunctive arcs at the same time. This is also very well known. We can let's say linearize the disjunctive formulation by the classical big M trick, which amounts in associating with each disjunction, each term in each disjunction, a binary variable y, which tells which one of the two terms will be satisfied in the final schedule, and then exactly one of these variables will be one at the end. And so you have a selection constraint which says this, that the sum of the y variables will be one. And then you have two linear constraints in the time variables and in these new y variables, so that if the first variable is one, then the first term basically collapses to the first constraint collapses to the first term in the disjunction, and if the second variable is one, the second term collapses to the second term in the disjunction, and the other term becomes redundant. So this is very well known, so I don't continue on this. In the end, the disjunctive formulation become the so-called big N formulation, and it's typically the most used formulation for solving train dispatching in the literature. There are alternative formulations like time-indexed formulations and even other type of formulations, but I have no time to go through this in this talk. So I will continue now on seeing how we can use the big N formulation to actually solve our practical problems. From now on, I will actually get rid of the selection constraints, in the sense that I will introduce the set capital Y of all binary vectors Y which are satisfying all selection constraints. So this is now the big N formulation where I got rid of the selection constraints, and instead I replaced them with this capital set Y. And for a given selection of Y bar in Y, I will denote by S of Y bar the set of terms selected by Y bar. And so associated with any such selection Y bar, I have now a new problem where all constraints are classical, are linear constraints, time precedence constraints in particular, and I call this problem sched of Y bar. note that when the objective function is a linear function, this problem is actually a very well-known problem, and it's a dual of a mean cost flow problem. So now, so big M formulations, as the one I just introduced, can be exploited to solve this train scheduling problem, but actually you will be able to solve only very small practical instances if you use this directly. Indeed, when the size of the problem grows, then we need to do something smarter. And this is what I'm going to describe in the next part of the presentation. So everything I said up to now was quite standard. The things I'm going to say after I hope will be new for at least for some of you. As I said, we can look again at our disjunctive graph and recall that in a disjunctive graph, every disjunction is represented by a pair of directed edges. And each of these edges is associated with a specific term in a specific disjunction of the original problem, which means also that I can associate one of the new y variables with each of these edges. So selecting a term in the disjunction corresponds to selecting an edge in a disjunctive arc, which means that any vector y is actually can also be seen as the incidence vector of a set of conflict edges in this graph. And I will call by S of y the set of conflict edges associated with a binary vector y. I mentioned before that when we solve the dispatching problem, we actually need to solve also a routing problem, which I neglected up to now, and I will neglect after this slide again. But I only wanted to say that the routing problem doesn't really pose any particular difficulty from the modeling standpoint, because it can be attacked by simply extending, let's say, the definition of this set, of the set Y, capital Y I just introduced. So in particular, I can introduce the routing edges. Again, these routing edges can now they are variable edges. I can select which edge I want to have, and then which means that I need to represent this with new variables, and also with new constraints saying which routing edges can be selected. These are typically multi-commodity flow constraints, and then I have to couple these new variables with all the selection variables associated with the disjunctive arcs. And this can be done with easy and simple, let's say, logic linear constraints. So the routing can be handled precisely in the same way as the class selections, but of course the problem practically becomes much harder to solve when you also include routing. Now, when you pick up a selection or a binary vector y bar in Y, in capital Y, then the disjunctive graph kind of collapses and becomes a standard graph. This is the graph I have drawn here, where the red edges are the one I picked up in each pair of each disjunctive arc. So the natural question is how this graph G of Y bar relate to the associated scheduling problem, sched Y bar. Well, these results are very well known, but I just recap them because we are going to use them later. So the first result says that it's a so-called feasibility result, and says that given a Y bar, the associated scheduling problem has a solution if and only if the G of Y bar does not contain a directed cycle C of positive length L of C. So, for example, in this figure here, the selection of edges I have chosen actually contains a cycle. You can see it, and the cycle has a positive length, which means that the scheduling problem will not have a solution. Here is an example of how this can happen in trains. It's a small example, but this can actually happen in more complicated examples. So assume that you have that the current time is 9 o'clock, and there are two trains here. The train I in its station here, but will leave at 9:10, precisely at 9:10. And this is represented in the graph by a pair of anti-parallel edges of length 10 and minus 10, respectively. Now, assume that there is also another train, J, coming in the opposite direction, and J can leave the station at any time from now. So it's not forced to leave at any time. But now, suppose that I make a mistake and I decide J wins the conflict with I on track D. So it leaves the station before I leaves the station. And both trains will take 15 minutes to run through track D. So it's obvious that since I will go out at 9:10, exactly at 9:10, there will be a conflict. And the two trains will meet on track D. And this is actually very visible on the graph, on the disjunctive graph, where I picked up the edge, the blue edge, from CJ to DI, representing the fact that J wins the conflict. And if I pick up this edge, then you see suddenly a cycle appears in this graph, and the cycle is of positive length, which means that the corresponding scheduling problem does not have a solution, as we know also from the practice. So now, suppose we consider now as a selection y bar such that G of y bar does not contain a directed cycle. Then there is it is well known that if we take first of all that we may assume that there is a path from O to any other node in this graph. And if we take the path with the longest length from O to U, the length of such path is actually feasible for the scheduling problem. And in particular, if we now consider a non-decreasing objective function, then and if we take the longest path from O to any other node in the graph, and we assign as a schedule exactly the length of such path to every node, then this solution is optimal for the problem associated with y bar. So this means that in case f is a non-decreasing function, then we are given the selection, then we can solve the scheduling problem by simply computing a longest path tree in the G of y bar. And so we can also say that we can define the cost of the longest path tree in G of y bar precisely as the cost of this schedule. So now we can, at this point, restate the original scheduling problem when the function f is the cost function is non-decreasing with cost with time. So what we want to find actually is a selection y bar such that G of y bar has no positive directed cycles, and the cost of the longest path tree in G of y bar is minimized. So having stated the problem in this form will allow us to actually construct a new type of formulation for let's say the scheduling problem, or if you want the train scheduling problem in this case, without the big N constraints, but at the cost of introducing many constraints. So the new formulation is based on this disjunctive graph that I introduced so far, with or without a routing, if you want. It doesn't change anything. So and you have a binary variable for each of the conflict edges, or each of the conflict edges and the routing edges, if you have routing. Then you have only one real variable, mu, representing the objective function. Then you have two types of constraints, the feasibility constraints and the optimality constraints. And the feasibility constraints correspond to the positive lengths directed cycles of G, while the optimality constraints correspond to the longest path trees of G. So the feasibility constraints, if let us denote by omega plus the set of positive directed cycles of G, then the feasibility constraints just state that for each positive directed cycle, at least one conflict edge cannot be selected. So this is a kind of logic, or if you want, cardinality constraint, and it's a very natural constraint in the binary variables of the problem. Then you have optimality constraints, and the optimality constraint says simply that if the cost of a selection y such that the G of y does not contain positive directed cycles is at least the cost of the longest path tree in G of y. And this is expressed by this kind of this cut here, this constraint here, which is very similar to the one we have seen before. So it's similar to a cardinality constraint, only that we have this constant here, which is the cost of the longest path tree. And also you have eta, which is the optimal, the value of the solution. Sorry, I think I used mu before. Maybe it is, no, it's eta. Okay, sorry. So the path and cycle formulation, just recapped here, it's very simple. You want to minimize eta, and then you want your y variable, the binary variable satisfy a certain number of feasibility constraints. And then you want eta and the y variable satisfy a certain number of optimality constraints. So it's very compact, but it contains many constraints, since in principle, the number of constraints can grow exponentially with the number of variables. So in order to solve this formulation, and actually also in order to construct this formulation, we use delayed row generation. So there is one interesting property that I want to remark here. So assume that the problem is infeasible. This means that there exists a certain number of let's say feasibility constraints which cannot be satisfied, correspondingly there exists a family of positive directed cycles, such that every solution y, every feasible selection y, contains at least one of the cycles in this family. When I say contains, I mean that y is a selection, y is the incidence vector of a selection of conflict edges, and then basically all the conflict edges in the cycle are contained in this selection. I will give you now an example of what I'm talking about. So again, we have our two trains and our mini network. So now suppose that again the current time is 9 o'clock, and train I must leave at 9:10, and train J must leave at 9:20. So both times are now fixed. It is sure that the trains will meet on D, and so basically the problem is infeasible if we accept this. And let's see what happens now in our disjunctive graph representation of the problem. Again, we have the two trains represented with the roots, and we have these timetable edges, which are pairs of anti-parallel edges, representing the fact that the two trains will basically arrive in D precisely at 10 or at 20. Now, assume that I wins the conflict. Then if I wins the conflict, then we basically are selecting the blue edge here. And you see that the graph will contain a cycle of positive length. The length is +5. Similarly, if we choose that J wins the conflict, then we are selecting this other blue edge from Cj to Di, the graph. And again, the graph contains a cycle C1 of length 25. So here is our family. So we have a family of two cycles, C1, C2, and any solution in the sense of any binary vector y in capital Y will contain one of the two cycles, in the sense that it will contain the conflict edge of the cycle, not of course the fixed edges, at the conflict edges. So why did I remark this? Because it would be very useful to actually attack our real-life pilot application, which I'm now going to describe. So basically, this project started with the problem of dispatching trains in real time in Oslo, in Greater Oslo Railway. Here you see there is a schematic representation of such a railway network. It's, as I said in the beginning, it contains a large station, Oslo Central Station, and 10 municipal lines incident to Oslo Central Station. So there are almost 1,000 trains per day. And basically, if you use all the formulations that we have seen up to now, it would be impossible to attack this problem practically. So what we needed, it was to introduce some more decomposition or reformulation. And this is what I'm going to describe in the final part of my presentation. So, the basic idea in this decomposition is given from a very, let's say, standard decomposition approach, which is used in practice by dispatchers, and which is normally denoted as a macroscopic, microscopic decomposition. So the idea is very simple. So you look at your network and you basically collapse entire regions and represent them as a single node in a new network that you can call macroscopic network. So you see here, this station here becomes this yellow node down here. This junction here becomes this blue node here. And then you have, of course, the line between the two nodes is represented by an edge, if you want. So once you have a solution for the collapsed network, then you, of course, are left with the problem of extending this solution to the original network with all the, let's say, stations and junctions re-expanded. And this is called the microscopic solution. Just to have an idea, if you look at the Greater Oslo network on the left, when you collapse it, you get the network on the right, where, for example, the large station of Oslo S is simply a big node, if you want, just a node. So the question is, so imagine if we are able to solve the problem with all the trains in the shrinked or in the collapsed representation, which means that solving means I have a schedule where I have all the arrival and departure times of the trains from all the stations which are now collapsed. So am I able to extend this solution to a micro solution? I mean, am I able to extend this solution to a feasible solution for each station in the line? So this is the problem I'm going to tackle in the next slides. How to do this? Just to have an idea what happens to the routes of the train when I collapse the network. Basically, the route of the train, it can be seen as a sequence of movements, or if you want, elementary tracks in stations and on the line. And what I do is it's simply to represent each of these, all these movements as a single node in the new macroscopic representation. So if we look at the constraint matrix of the original, for example, big M formulation of the problem, we can see that it actually presents a very convenient quasi block structure. Indeed, we can group all the constraints associated with the stations and all the constraints associated with the track lines between the stations. And what we see is that so the blue group of constraints are those associated with the line, and the red group of constraints are those associated with the stations. And the interesting thing is that these constraints, they only share a very small numbers of continuous variables, which are the timetable variables, which are the times where the trains enter and exit the stations on the railway. No binary variables are shared. This is also very interesting. And the objective function is actually only in these variables, because in the timetable variables, because basically what we measure in the objective function is the delay with which trains arrive at stations. Another interesting thing is that if we only look at the red part, so the constraints associated with the stations, they also decompose perfectly into a block of constraints associated with each station. So we are going to use this property. And in fact, if we now look at the entire formulation, we see that basically we can reformulate it in the following way. We can drop all the constraints associated with stations and keep only the constraints associated with the scheduling on the line. And then we basically substitute the constraints on the station with cuts or other constraints, which are only in the binary variables and in the timetable variables, which we may call logic Benders cuts. In order to construct this reformulation, we will need an algorithm, and this is actually done by a classical master-slave algorithm. So I just quickly go through this algorithm now. So what we do is we start solving a master problem, which is without any additional cut. And then we get a solution, and in particular in this solution we get all the timetable variables. And then we solve the Slate problem, which amounts to decide if these timetables are feasible for all the stations in the network, and which means I can solve one problem independently of each other for each station, and then I can check if the solutions, if the timetables are feasible or not. So if they are feasible, this means that we have a complete solution for the entire network at the micro level, if you want, and the solution is optimal because it was optimal for the restricted master. But if it's infeasible, then we need something to avoid let's say, to cut off this solution. And this is what it's called a logic Benders cut. And I will show now next how these cuts can be actually derived. So, as I said before, the Slate problem now amounts in deciding if the timetable produced by the master program is feasible for every station. And if it's not, then we need to produce a cut or a constraint which actually, let's say, cut off the current timetable. And to do this, we exploit the feasibility conditions that we have, let's say, described when we described the pattern cycle formulation. Namely, so if we look at the individual station problem, we are given the arrival and departure times of each train in such station. This is the timetable produced by the master program, which we must find out if it's feasible or not. And so associated with the station problem, we have a disjunctive graph, exactly the graph we have seen in the previous slides. And of course, this disjunctive graph will contain all these timetable edges, which represent the current timetable given by the master program. Now, if the instance is infeasible, this means that we have seen it before, that for any possible, so that the graph G contains a family of cycles bar or omega bar of positive lengths, such that every selection Y contains a cycle in the sense that I said before. Now, suppose now that we pick up a cycle in this family, and suppose that C contains a timetable edge. One can actually show that the family of such a family of cycles must contain at least one such cycle. And if it contains a timetable edge, this means that it contains also the origin O. then it contains 2 timetable edges, and exactly 2 timetable edges. For example, we can just to fix the idea, we can assume that these 2 timetable edges are actually associated with the arrival of 2 trains at the station, train I and train J. And we may also assume that the one associated with train I is the edge with a positive length TIA, and the one associated with train J is the edge with negative length minus TJA. Then I said that the cycle belongs to omega bar, which means that the length of the cycle is positive, which means that if we look at if we consider the difference between TIA and TJA plus the length of the remaining part of the cycle within the station, this is positive. In other terms, the difference between the arrival time on train J and the arrival time on train I is less than the length delta of the rest of the cycle. So if we would like to prevent this cycle to be positive, then we need a timetable which actually satisfies the constraints that TJA minus TIA must be at least delta, because otherwise this cycle C would be negative. Remember that the timetable is produced by the master program. So we should introduce this constraint into the master program if we want to avoid this cycle to be positive. Actually, we don't have only one cycle, but we have a family of cycles. And so if we look at the entire family of cycles, we don't need, in some sense, to kill all these cycles. It's enough if one of these cycles becomes non-positive. So actually, what we need to produce is a disjunctive constraint, in which I precisely say that either the first cycle is non-positive, or the second cycle is non-positive, or the third cycle is non-positive, and so forth. So basically, what we have produced is again a disjunctive constraint, but a disjunction of very simple constraints, which are the time precedence constraints. So this is basically a disjunction of the same form of the disjunctions we use for the selection constraint of conflict edges, but only with the only difference that it has many more. It can have many more terms, one for each cycle. So the full reformulation will be now this type. So you have a part of the formulation which is related to the macro problem, which is basically related to the problem just associated with the tracks between the stations, and then you have all these logic Benders cuts, which are disjunction of time presence constraints, which in turn can be linearized with the usual big M trick. So I don't go into the details. The point is again to add new binary variables, one for each of the terms in this possibly long disjunctions. So I'm basically done. With this technique, we were actually managed to tame the problem in dispatching trains in Oslo S. So what we did, at the current in the current phase of the project, we actually applied another level of decomposition by decomposing into the big station, the large station of Oslo S, and all the lines incident into Oslo S, and solve them separately, and then rejoining them at the end. So what you see here is actually the output of the problem. So the thing that is shown to the dispatchers. And if let me try now to share a different slide, if I can. I can show you in what we can do here, maybe. Sorry, how much time do I have?
As much as you need, right? So, but typically people speak like for 50 minutes, but you can speak a little bit more.
Okay, so I still have 0 minutes.
But you can finish your idea. That's not.
I just wanted to show this. This is just fun. I mean, it's just to show what we do in Oslo if I find it. But apparently disappeared after we did all the experiments. So I should restart it. Just a second. If okay, I can show it here on the slide. So basically, what the dispatchers see, at least the dispatchers which are taking care of the lines incident to Oslo S, is a train graph, which is something like you see here in this picture, and it's nothing more than a Euclidean plane with some lines. Every line corresponds to a train, and basically it's the trajectory of the train through the stations of the line. So on the y-axis you have the space, so the stations, and on the x you have time. And the blue line, the blue vertical line here represents now, so the current time. Everything on the left is in the past, and everything to the right of the blue line is in the future. So what you see on the right is actually what our algorithm predicts, or let's say decides, because the algorithm must decide where trains should meet on the line, because this is a single track line. These are mostly single, not all, but mostly single track lines. And so they need to meet in stations. Okay, so I may conclude here.
Okay, so thank you very much, Carlo. It was really as practical as I expected. And before I unmute all the others, I will ask one initiating question. So I see really many similarities with classical production scheduling problems. So for example, I wonder if that routing problem where you have in fact two parallel segments of the track, whether you can't represent them as parallel identical processors. So to say, for example, I have some resource type and it has capacity 2, for example.
Yes, indeed. We at some point we actually had started the project with a pharmaceutical company to do precisely this, but then the project, for some reasons, it didn't continue. But of course, these ideas can be extended to production, as you said, and to parallel machines, and to capacitate the.
Yeah, and do you have, for example, in your train scheduling problem, do you have also problems like setup times or other that are frequently found in production? For example, when one train enters some segment, then do you need to reconfigure something on that segment, for example, or? Yes,
indeed, you do. You have things like buffer times, so in particular, when you have, depending on the train that you have in front of you, you may have different times before entering the track. You know, so these are also called release times. I mean, in the sense that the tracks must be, not in the sense of the classical scheduling problem, but that the track must be released by the previous train. And so you have a lot of these details that, of course, I didn't describe in the presentation because I wanted to basically focus on the methodology and on the decomposition. So
how far is it difficult to join your problem with personal scheduling, because there are drivers obviously and they have their working, maybe not shifts, but some constraints on how long they are supposed to drive, and that can become extremely complex in relation to this human constraints, let's say.
Absolutely. This is another issue that we are tackling, but not so much in Europe, while in America it's maybe even stronger, the problem, because there they have really very long stretches to run trains, and it may happen that your crew at some point in the middle of nothing should basically stop, and they really stop. So they basically get off the train, and the train can stop there. So it's actually from the practical standpoint a very important problem. But these problems actually they are decomposed typically. So first you tackle the train scheduling problem, the train timetabling problem, and then you solve the crew scheduling problem or the rostering problem, depending on which level you want to do. And it has been tackled by several researchers in the literature. So
okay,
we didn't look at it.
Okay, so I allowed participants to unmute themselves. So if anybody wants to ask question, please go ahead.
Okay, may I ask one question, if you can hear me?
Hello, Alessandro.
Yes, you can hear me. Okay, so hello, Carlo. Very nice talk indeed, very informative. Well, at the end of this talk, I think one thing which would be interesting to know is, so what's next? In the sense, what do you see as a challenging open problem in this area of railway scheduling, or more generally in the area of scheduling problems in which can somehow be reduced to the problem of selecting edges on a directed graph, because in the end it seems that the core of your model is the fact that by selecting the right set of edges you can solve a certain amount of different problems.
Yes, thank you for asking this. I completely agree with you. I think one of the messages of this presentation is that the scheduling problem is actually an edge selection problem. So you have a graph and you want to select some edges following certain constraints, and with some and if your objective function is what typically in scheduling problems is called the regular objective function, then once you select the edges, basically your work is done, because what you need to do is only to compute a longest path tree in a graph. So there are many problems that can be formulated in this way of course one big problem is to be able to extend these results also to larger instances. It's the same usual problem. So as soon as the instance grows, then all your decompositions will fail. And it happened to us that the algorithm was stuck in some cases because the situation became too congested. So in that case, typically what you do, you resort to some heuristics approach, but you still use this underlying, let's say, integer programming formulation and properties of such formulation. But you need to resort to some kind of heuristic in order to tackle that. So, but and another interesting chapter, I would say, is the use of time-indexed formulation for these problems, because we know that time-indexed formulations have a much better, let's say, relaxation compared to big N formulations. And but what happens there is that the size of the instance grows very much. So there is a new family of time-indexed formulations called DDD, the Dynamic Discretization Discovery, introduced by Salzberg and some of his students recently. And I think they look very promising, because they are very good to keep at bay the number of variables you produce, and also at the same time they allow you to produce the lower bounds along the way rather than upper bounds, which is the usual thing with time-indexed formulations. So I think the next challenge would be to really try to look at these formulations and try to work with time-indexed formulations, which provides such stronger bounds.
Okay,
Thank you.
Any other question? There is one question in the chat, if you can take a look in it.
The presentation, what size of instances can your algorithm solve in a reasonable time? It's a good question. So the size of this network, which is a Greater Oslo network at the moment, is a size that I can. I'm confident we can tackle. We actually tackling it. So I know we can tackle this, which means basically we have circa 1,000 trains a day in a normal day, and as you can see, there are many stations, but most of them are small. There are only 3-4, let's say, medium-sized stations and one large station, which is Oslo S. Oslo S contains 20 platforms, and there are some junctions which are really congested and complicated, but which contains maybe only 5 or 6 parallel tracks. So So this is more or less the size of the I don't think we can solve larger instances at the moment with these techniques, of course, that I introduced.
Okay, there is another question in the chat.
May I ask that are you going to use meta-heuristic algorithm in this problem? Well, let me say that I'm not so obsessed by this distinction between heuristics and non-heuristics. Algorithm. After all, also integer programming is a heuristic when the size grows, because you cannot solve any instance with integer programming. So you need to resort to the heuristic part of the integer programming approach, and this is what we are doing. So yes, definitely, we are going to use meta-heuristics, math heuristics, even all the heuristics which are already included in classical solvers and so forth. We are not, we can't avoid to do that. It can be considered as an NP-hard problem for larger size. Well, it is the fact that the nature of the problem, of course, the problem is NP-hard for any size, let's say. It doesn't depend on the size. Actually, if you fix the size, then the problem is not NP-hard anymore if you want. But what practically this means that if the size grows a little bit, then it becomes more and more intractable. But the challenge is exactly this. I mean, how to make an intractable problem tractable. After all, I mean, these problems are solved every day by human beings in real time. So it must be possible for a good algorithm to tackle them as well.
Okay, so the last call. Is anybody willing to ask the question?
Yeah, actually, if I may.
Sure, go ahead.
So I actually have two questions. First of all, I would like to say I find your methods and study very interesting. The first question I have is...
Who's talking?
It's Hatice Çalık.
Nice to meet you.
Nice to meet you too. Thank you very much for this very interesting presentation. So on slide 22, I realized that you have decision variables like YUV, YZU, two groups of decision variables or two types of decision variables.
Sorry, which one is the slide?
Slide 22.
I don't see the numbers, unfortunately, now. So
there was a number on that one. If you keep going.
And formulation.
Yes. Yeah. No, too far.
No, now it's too late. Just we have to wait. Okay, let me.
On lower right corner, you have numbers.
Do I?
Yes.
Yes.
Go ahead.
Slide 22.
Yeah.
Yes. Okay, I didn't really delve into this because it's a very standard.
Yeah. I'm not. Maybe it doesn't matter. But
no,
do you need?
Yes.
Do you need to define like two different decision variables? I mean, do you need this constraint that says YVW plus YZU equals 1?
No, absolutely not.
Right, because you
Right.
can just say that if one of them, if this one of these variables takes value 1.
Yes.
Yeah. Right. Yeah.
Oh, absolutely. I mean, the fact that you don't need it, it's actually expressed by the fact that you have an inequality there, right? So any of the two variables can be actually eliminated from the problem.
Yeah.
And you can have only one of the two if you want. But the reason why I introduced two variables, it was precisely to basically clarify this, the fact that you want to pick up an edge. So if my computer starts to work again, yes. So the main point is this. It's in this figure, and if you want in the next one, because I want to have a variable for each edge, for each confit edge, and that's the only reason. I think it makes everything much clearer.
Yep. And my second question was about the decomposition type you utilize. You use logic Benders decomposition instead of classical Benders decomposition because you have continuous decision variables. You could indeed go for the classical one, but you chose to use the combinatorial Benders cut. Was this like an intuitive decision? I mean,
no, absolutely not. Actually, I must tell you the whole truth. If you notice that I call the initial, I mean, we have two decompositions here, if you want. The first one is the one which led to the so-called path and cycle formulation. And the second one is the one I used in order to generate, let's say, the macro decomposition of the problem. So these are two different things. And if you look, if you focus on the first one, so the path and cycle formulation, there I used, if you see, there are two types of constraints, right? Feasibility constraints and optimality constraints. Well, maybe this reminds you something. These are precisely the constraints of the classical Benders reformulation. The only difference here is that if you want to try to get, let's say, derive these constraints from the classical Benders reformulation, then you have to go through, let's say, the dual of this problem here with the big N constraints, if you want. Yeah, then you can do that, but the problem is that you get very weak constraints. So in order to get the final constraints of the path and cycle formulation, you can actually derive them from the classical Benders optimality and feasibility cuts, but then you have to strengthen them. So you can see that these constraints here are actually the strengthening, and if you want, also the lifting of the original Benders cuts obtained from the big N formulation of your original disjunctive formulation. I don't know if I answered your question. Yeah, for the second class of constraints, well, I didn't even try to do the classical Benders reformulation. I think that would not really lead to anything. And there are actually works in the literature, for example, Pellegrini and others, they tried actually to apply directly the cuts obtained from the Benders reformulation, but they admitted it didn't go anywhere. And the reason was, I think, that they were too weak. So you actually have to do what I did here to strengthen them. And at the same time, actually, this is called the path and cycle formulation, but the optimality cuts in this formulation here, they are associated with trees. You may still strengthen these formulations further by kind of disjoin the trees into the paths of which make the trees, the longest path tree, and obtain even stronger formulation, where the optimality cuts are associated with paths and not with trees.
Thank you very much. This was really inspiring, I must admit.
There is one other related question to it in the chat.
Let me reopen the chat. I lost it. But are you still sharing? Am I still sharing? Yes, I am. Okay. It seems that the Slate problem in an IP problem, how do you find dual variables to generate feasible cuts? I have to read again the question. How do you find? No, this is why. Now let's talk about the second, the final, the macro decomposition. I guess you're referring to this point, and let me go there. So this is why they are called logical Benders cuts and not classical Benders cuts. So I'm not using any dual solution to construct the cuts. But what I'm doing is actually precisely what I described here. So let me again. Okay, so what I'm doing is actually identifying the cycles in this family, and this is done by the iterative row generation approach to the path and cycle formulation. So basically, you formulate your problem, your instance, and you try to find the feasible solution to your instance. And if there is no if there is no feasible solution, that means that there is this family of cycles, and you identify the family by iterative delayed row generation. And then once you have the family, you also have the cut, because the cut is basically, let me see if my mouse starts again to work. Yes, the final cut is the disjunction of constraint associated with one cycle in the family. So we are not going to, we are not using dual variables here. Or
It's
I don't know if I answered.
so a solution you do cycle elimination, right?
Yes. And we actually, in order to identify the cycles, we do a delayed row generation. So we solve the problem, we find a feasible solution, but this solution is feasible only for the current restricted problem. And then it may happen that there are still cycle constraints which are violated by your solution. Then you add this cycle constraint until you get either a family of cycles or you find a feasible solution.
Okay, so Carlo, thank you very much for your talk and for your answers. I think it's really a rich research domain, which has really nice applications. By the way, I arrived by train today. And let me speak about the next talk. Next talk will be given in 2 weeks by Michel Gendreau from Polytech Montreal. And he will speak again about transporting problems, in his case about vehicle routing with time windows, which is, I think, formally a little bit close to similar representation we have seen today. So thank you very much for being with us, and hope to see you in 2 weeks. Bye-bye.
Yes. Bye-bye. Thank you very much.
Bye-bye.
Thank you.
Bye-bye. Thank you. Thank you.
Thank you.